Welcome back. Today, we're diving into one of the most fundamental tree structures in computer science, the binary search tree, also known as BST. So what is a BST? It's a hierarchical data structure where each node has at most two children, a left child and a right child. But here's the magic rule that makes it a search tree. For every node, all values in the left subtree are smaller and all values in the right subtree are larger. This simple rule is what makes searching incredibly fast. Let's understand the structure first. Each node contains three things: the data value, a pointer to the left child, and a pointer to the right child. The topmost node is called the root. Nodes with no children are called leaves, and the longest path from root to a leaf determines the tree's height. Now let's talk about the main operations. First, insert. You start at the root. If your value is smaller, go left. If it's larger, go right. Keep going until you find an empty spot. That's where your new node goes. Second, search. Same logic. Compare your target with the current node. Go left if smaller, right if larger. If you find a match, great. If you hit null, the value doesn't exist. Third, delete. This one's a bit tricky. There are three cases. If the node is a leaf, just remove it. If it has one child, replace the node with that child. If it has two children, find the Inorder successor, which is the smallest value in the right subtree, replace the node's value with it, then delete the successor. Now let's talk about traversals, different ways to visit all nodes. Inorder traversal visits left, then root, then right. This gives you values in sorted order, super useful. Preorder goes root, left, then right, good for copying the tree. Postorder goes left, right, and then root, used when deleting the tree. And level order uses a queue to visit nodes level by level. That's BFS style. What about time complexity? On average, search, insert, and delete all take O of log n time. That's because you're cutting the search space in half at each step. But here's the catch. If the tree becomes skewed, like a linked list, the worst case is O of n. That's why we have balanced trees like AVL and red-black trees. Now let's quickly look at the code. In C, we define a struct with data, left pointer, and right pointer. The insert function recursively finds the right spot. If the value is smaller, we go left. If it's larger, we go right. When we hit null, we create the new node. In C++, we wrap everything in a class with a private node struct. We use templates to make it generic. The logic remains the same: recursive insert and search. In Java, similar structure. We have a node inner class, and the insert mech handles the recursion. The search function returns true or false based on whether the value exists. In Python, it's cleaner. We define a node class and a BST class. The insert method checks if root is none, otherwise calls the recursive helper. Same pattern for search. In JavaScript, we use ES6 classes. The insert can be done iteratively using a while loop, which is a nice alternative to recursion. Search works the same way. All these implementations follow the core logic: compare, go left or right, and repeat. Where are BSTs used in real life? Database indexing to quickly find records, file systems to organize directories, autocomplete features using trees, which are tree variants, expression parsing in compilers, and many more. So, to wrap it up, a binary search tree organizes data in a way that makes searching, inserting, and deleting efficient. The left smaller, right larger rule is the key. Traversals help you visit nodes in different orders, and all operations run an O log n time on average. If you want the best animated tutorials on data structures and algorithms, check out algopk.com. We make learning visual and easy to understand. Thanks for watching. See you in the next one.